In a previous lesson, we have tackled the substitution method with antiderivatives or with indefinite integrals. Now we're going to be looking at the substitution method with definite integrals. For example, here we have the integral between 0 and 1 of x into x squared plus 1 all cubed. Now, it's good to revisit the other lesson on the substitution method in order to recall how it really works with indefinite integrals. However, over here, by looking at this function, we notice that we have in the integrand, in the function that we're actually integrating, we have a power. So by looking at the base of the power is x squared plus 1. Now the derivative of x squared plus 1 is 2x. Now we notice in the integrand we have an x. So we do have in this integral x multiplying dx. So we almost have the derivative of x squared plus 1. So we could use the substitution method by setting u equals to x squared plus 1. So over here, du would in fact be 2x times dx. Remember that du is in fact defined by u prime times dx because u prime is du over dx according to Newton's notation of the derivative. So whenever you are dealing with or you are working with du, the differential that corresponds to the variable u, now that is the derivative of u times dx. However, you'd notice that in the integral we have x multiplying dx, so we divide both sides by 2 in order to have x times dx in terms of du. Now remember, this only works when they differ by constants. So over here, x times dx in the integral is replaced by half du. So if I were to call this integral I, so going back to I would in fact have I to be equals to half times the integral of u cubed times du. Now over here, since we are dealing with a definite integral, we have a bound here. It is defined over a given interval, which is in this case is 0, 1. However, 0 and 1 are values of the variable x since they're the bounds of the integral in terms of x. So I cannot consider 0 and 1 to be the bounds of the integral in terms of the variable u. That would be mathematically wrong because 0 and 1 are values of x. They're not values of u. However, what we would do here is determine the bounds that corresponds to the variable u as images of 0 and 1 with respect to the function u equals to x squared plus 1. So over here, for x equals to 0, what is u? u is 0 squared to 0 plus 1, which is 1. And when x is 1, 1 plus 1 is 2, so u would in fact be equals to 2. So the bounds of the definite integral corresponding to the variable u are 1 and 2. Now keep in mind that the image by u of the lower bound is in fact at the lower bound of the integral in terms of u, and the image of the upper bound is at the upper bound. Even if when you evaluated the new bounds, the lower bound ended up being greater than the upper bound, it's okay, but to be mathematically correct, the image of the lower bound should be at the lower bound and the image of the upper bound should be at the upper bound. So now I'd evaluate the definite integral between 1 and 2. So that would be half times. An antiderivative of u cubed is 1 over 4 u to the 4 between 1 and 2. So I would in fact be half into. Now 2 to the 4, upper bound minus lower bound. 2 to the 4 is 16, so that is a 16 over 4 minus, at the lower bound it's 1 over 4. So that is a half times 15 over 4, so that leaves me with 15 over 8. So you'd notice here that by evaluating or by changing the bounds to correspond to the variable u, you did not really have to go back to the antiderivative in terms of x the same way you would do whenever you're using the substitution method with indefinite integrals. With indefinite integrals, if you did not have bounds corresponding to the integral, after you find 1/8 u to the 4, after you have found the antiderivative, you'd have to replace u back by its expression in terms of x to give the antiderivative in terms of x. However, when you're working with definite integrals, you don't really have to go back to the expression of the antiderivative in terms of x if you've already changed the bounds and found the bounds that correspond to the variable u. And that is because you've already evaluated u at x equals to 0 and at x equals to 1. However, if you do not wish to change the bounds, so over here, you could just work on finding the antiderivative of the function all the way to its expression in terms of x, and then replace it or evaluate it between the bounds corresponding to x. What I would mean here is that over here you'd look at for the antiderivative of the function, which is half u cubed, the integral of u cubed times du, which is equals to half of 1/4 u to the 4 plus k. So over here, since you have not changed the bounds, you notice that we're working with an indefinite integral. We do not consider the bounds here to be 0 and 1 when the integral is defined in terms of u. That is mathematically wrong. So we'd work with the indefinite integral, and we'd look for the antiderivative. So that is 1/8 u to the 4 plus k, which is 1/8 x squared plus 1 to the power of 4 plus k. So now that I have found the antiderivative in terms of x, now I say then I is equals to that antiderivative between 0 and 1. Since the variable of the antiderivative here is x, now I evaluate it between 0 and 1, but these are not equal. So if you do not wish to change the bounds, what you could do is evaluate, or in fact find the antiderivative in terms of x, then go back to I and evaluate that antiderivative between 0 and 1, which are the values corresponding to the variable x. However, changing the bounds does quicken up the process. So this is why I'd urge you to always change the bounds and find the values of the bounds corresponding to the antiderivative in terms of u. In that case, you could immediately evaluate the definite integral without having to go back to the variable x.